Dear student, today's topic is junction field effect transistor, and the code is ELEC-SPD-S1A, Electronics Special Devices, section 1A. Junction field effect transistor, as its name indicates, there is a field effect phenomena. It is different than the bipolar junction transistor BJT, which we have studied earlier. We will come back to this figure, but before that, let's go through that first figure. Junction field effect transistor, what we have. Let me go to the junction field effect transistor, or JFET, is a voltage controlled 3-terminal unipolar semiconductor device available in N channel and P channel configuration. I will discuss the basic theme behind it, that how this device work. Okay, here we have got the typical two types. We have got N channel and P channel. So we have got in field effect transistor, we have got one single bar of N channel semiconductor material, and this are the one single bar of the P channel semiconductor material. We will discuss first. Let's say take the N channel, and what we do, we do P type semiconductor material on the opposite faces of this bar, and we join these two P type with a ohmic contact, and we call it gate terminal, while the other two terminals, one is called the S, or the source terminal, as here it is written, and this one they call the drain terminal. So it has got the although it is a unipolar, yes, you can see on one type of the charges are flowing, N type, which is the electron in this case, and P type in this case, holes are in this case. So here we have got the P type 2 opposite polarities to the main N channel bar. This is the main bar, which is the main current will be flowing in this main bar. So we call it channel because the path, there is a path, it will be controlled. The path will be shrunk, or it will be allowed to expand according to the voltage applied across the gate. So that is the construction of it. We will see the thorough construction as well. And this is the symbolic notation for the N channel. You can see the arrowhead is going into the plate, and the other two are the drain and the source. So drain, the polarity, the potential is applied such that from positive to negative to the source, and the gate polarity is kept negative in case of the N channel bar, and it is kept positive in case of P channel bar. Similarly, you can see the other version, which is a P channel. We have now the pointing outward, the gate, we call it the current, which is IGSS. In this case is also the I gate source to source, the current which is flowing through, and similarly here the IGS is this again the gate to source current is flowing. So in this case it is the outward arrow, rest is, you can see this is a straight plate, and here we have angled the terminal. In case of this is right angle 90 degree making this terminal. In case of if you remember BJT, we have just a slanting angle the terminal, and was extended outside. So this is the basic the diagram or the construction of the field effect, junction field effect transistor. It makes, you can see the one junction of each the P type with the N, so it's called junction field effect transistor. Let's go up again I'll start with the basic or the detailed the diagram. So here is the similar, but in the actual which how it is formed uh, basically. So what we have got here, we have got the p-type gate, which is on the one side the same, and the other one, actual, consider we have the almost covered the whole of the bar, or you can have the partial covering as well, and potential is applied. This is the gate, and these two both are interconnected together, and this is the drain and the source is the ohmic contacts. We might have the here only the p-type, we might have the drain this side or the source this side, but this is actually practically when the wafers or the silicon chips are fabricated. The actual situation is similar to this one. So what we have, there's a field around it, P. This is we call it the depletion layers, because when this plate is reverse bias, so obviously what we will get between n type and p type, this is a junction, it will expand in the reverse bias. Similarly, this junction will also expand, which will called an field effect, because of the reverse biasing of these two p-type junctions will make the channel narrower. Narrow means the smaller area of cross section will be available for the flow of the charge if the source and the drain is applied a voltage. So from positive to negative, if you see the drain current is flowing through, but if we make this p-type here, the gate is less positive, so the depletion regions of the respective junction will shrink back, go back to the close to the junction, and we have more area of cross section of the n channel where the negative electrons will be available and the larger current will be flowing. So this is the basic theme behind it. So you just read through, all these things are written in this whole this PDF document, and you will be finding. Let me just quickly go through in bipolar junction transistor tutorial. We saw that the output current of the transistor is proportional to the input current flowing into the base terminal of the device, thereby making the bipolar junction transistor current operated device. So as a smaller current can be used to switch a large load current. The field effect transistor, however, the field effect transistor or simply FET, however, use the voltage that is applied to their input terminal, and it's called the gate, to control the current flowing through them, resulting in the output current. So I have given you the basic theme, so you read it out. The same basic theme is discussed in this case. I will diagram which we earlier saw that the drain current was very fluently flowing through, but when we apply the gate voltage over here, which is the highest voltage, let's say -2, and these two regions are touching almost, the fields, reverse bias fields are touching each other. Now the channel is almost closed. Okay, so current is at this particular stage, we call the JFET channel is pinched off, means that voltage is equal to 0. So that is the typical the equivalent model, JFET model, that drain to source there is a resistance which is controlled through the gate diode. This is the PN junction diode, obviously p-type and n-type of the channel, and that is controlling the resistance by the biasing of the diode or the field across the voltage across that diode. So the next slide we will see that these are the similar output characteristics curve, which is between the VDS, voltage applied. This is the VDS, which is voltage being applied across the drain to source. This is ID, which is the drain current flowing through. So similar, you can see this is the gate voltages, voltage between VG, gate to source, which is 0. At 0 we can see the highest drain current is flowing through. As we increase the gate voltages with a negative polarity, we can see the drain current is falling off very quickly. And we have, this is the saturation region, this is the pinch off region, where the -4 volt is the gate voltage, which is the maximum reverse bias voltage, and the two fields are touching each other and cutting the channel flow to the drain current. So that is the output characteristics curve of the field effect, junction field effect transistor. This is the circuit diagram, how we apply the plus minus. This is VDS voltage we have applied, and this is the gate voltage we applied. This is the typical the transistor, the N channel transistor, JFET transistor. So there are further other regions are explained. You can read them and you can find the relevant descriptions or the details. Now let's come to the formulations. The drain current is given by this ID is equal to IDS 1 minus VGS by VP whole square. So that is the pinched. Note that the voltage value of the drain current will be between 0 pinched off and the DSS maximum. The drain to source channel resistance is given by this VDS into the delta VDS by delta ID. From the curve we can get, which is 1 over G, which is the conductance, where G is the transconductance, since the JFET channel voltage control device, and which represents the rate of change of the drain current with respect to the channel in the gate source voltage. So modes, there are again similarly, as we have got the common emitter, common collector, common base modes. Similarly, we have got the three modes as well. The common source configuration. This is the, you can see the common source is common. This is configuration. Common gate configuration. The gate is common, is equivalent to the common base. It is equivalent to the common emitter. And the last one is a common drain or the common collector, which we have in case of the bipolar junction transistor. So these are the three modes of the configuration of the JFET. Now the JFET as the amplifier, we have the relevant relations. Again, this is the self bias. You can see the 4 resistors. You can, same techniques are applied at which we have studied in the BJT transistor amplifier. So that is the which we have the common in this case is the source, common source amplifier. We have input three resistor which is controlling the drain gate voltage, and this is the drain current. Obviously the polarity has to be kept accordingly. The reverse biased, it can produce a reverse bias field. So the Vs is equal to ID RS, and Vs is equal to Vg minus VGS. Vs, remember, S is for the source, D for the gate, and D for the drain. You can work that out very simply from the circuit. So this is all about the field effect transistor, junction field effect transistor. I hope you have done the basic construction and its operation. With this we reach to the end of the slide. Thank you.